Welcome to this explainer. Today, we're unpacking a massive breakthrough research paper that essentially turns a highly complex mathematical problem into a high-stakes cyber thriller. We're looking at a concrete treatment of Fiat Shamir signatures in the quantum random oracle model, which comes to us from researchers at the University of Amsterdam, Quafoft, and IBM Research. So let's dive right into this super provocative question. As quantum computing becomes a reality, are the digital signatures protecting our entire internet already fundamentally broken? I mean, think about it. Every single time you download software, sign a digital contract, or even just securely browse the web, you're relying on cryptographic signatures to prove identity and prevent tampering. But there's a huge paradigm shift looming on the horizon, and it's threatening to completely unravel the math that keeps those signatures secure. Section 1. The Quantum Security Threat. Why classical cryptography is on notice. To really set the stage here, you've got to understand the impending threat to standard cryptography and why the entire cybersecurity world is basically on edge right now. Institutions like NIST are actively scrambling for post-quantum solutions, and for a very good reason. Quantum computers operate fundamentally differently from the classical computers we use today. They can actually execute offline primitives, like the hash functions embedded deep in our security protocols, on arbitrary superpositions of data. What does that actually mean? It means a quantum adversary doesn't just sit there guessing one password or key at a time. No, they can query a vast sea of possibilities simultaneously, entirely bypassing our traditional cryptographic defenses. Section 2. The Mechanics. Fiat Shamir and the QROM. All right, to fix the machine, we need to know exactly how its gears turn, right? The Fiat Shamir transform is literally the foundational bedrock here. Developed way back in the 1980s, it's essentially this really neat cryptographic trick for translating a back-and-forth authentication protocol into just a single, verifiable digital signature. It takes an interactive conversation where a prover proves who they are to a verifier and flattens it into a non-interactive mathematical stamp of approval using a hash function. And this brilliantly illustrates the three-move canonical identification scheme at the very heart of that transform. Think of it kind of like a secret handshake. Step 1, you make a mathematical commitment. Step 2, I issue a random challenge to test you. And Step 3, you provide the mathematical response. If your response matches your initial commitment, boom, I know you hold the secret key. Now, in an honestly generated transcript, the prover generates a state and a commitment, the verifier sends a challenge, and the prover responds. This whole back and forth results in either a perfectly valid signature transcript or, if something goes wrong, an abort. The Fiat Shamir transform basically automates the verifier's challenge using a hash function, making the entire process completely self-contained. But here is the kicker. There is a stark, undeniable contrast between our classical understanding and our new quantum reality. Standard schemes are proven totally secure in what we call the classical random oracle model, or ROM. But, and this is a big but, that does not guarantee security in the QROM, the quantum random oracle model. In the QROM, adversaries aren't just making standard queries anymore. They can query the hash function in quantum superpositions, opening up entirely new, crazy avenues of attack that our old classical proofs simply cannot account for. The absolutely critical vulnerability here is something called rewinding. See, in classical security proofs, researchers use a neat trick called the forking lemma. It basically lets them rewind an adversary, literally go back in a proof's history, and give them a completely different challenge, just to extract their secret key. But quantum computers, they completely break this. Because of the fragile nature of quantum states, you can't just perfectly rewind a quantum adversary without collapsing their state entirely. Adaptive reprogramming in the QROM is incredibly difficult, which essentially renders those old classical proofs practically useless. Section 3. The Framework. The Lossy Key Solution. So if we literally can't rewind anymore, how on earth do we prove these systems are safe? Well, enter this breakthrough paper. The authors set out to create a generic, completely modular framework for constructing what are called tight reductions in the QROM. A tight reduction basically means that breaking the signature scheme is exactly as difficult as solving the underlying, incredibly hard mathematical problem itself. There's zero wiggle room. The absolute heroes of our story here are lossy identification schemes. This is such a fascinating concept. A lossy scheme has an alternate key generator that creates a lossy public key. And to a computationally bounded quantum adversary, this lossy key looks absolutely 100% indistinguishable from a normal true public key. They literally cannot tell the difference at all. When you use this lossy key, the whole scheme achieves what we call statistical soundness. What this means in this impersonation game is that even if we imagine an unbounded, basically infinitely powerful quantum adversary, they still cannot successfully impersonate a prover. There simply isn't enough information in that lossy key to fake the signature. It mathematically slams the door shut on forgeries. To completely bypass that pesky need for rewinding, the researchers broke the security proof into 3 really simple, elegant steps. First, the lossy property guarantees security when the attacker has intercepted exactly 0 signed messages. Next, a clever little trick proves security for 1 intercepted message. And finally, by de-randomizing the signature generation using a pseudo-random function, they lock down full airtight security against advanced chosen message attacks. They effectively fixed the whole rewinding problem by making the entire proof history-free. It's brilliant. And this whole sequence proves a totally vital point. Shifting away from probabilistic signatures, where random numbers are just generated on the fly, and moving toward deterministic signatures, where the randomness is strictly derived from the message and the secret key, creates a gold standard tight reduction. To put it as simply as possible, because of this tight reduction, the deterministic version is exactly as secure as the hard underlying math problem it's built on. If an attacker wants to forge a signature, they literally have to solve the foundational math problem itself. No shortcuts. The standard probabilistic version, on the other hand, suffers a massive quadratic blowup in its running time during the proof, making it non-tightly secure. So deterministic is clearly the way of the post-quantum future. Section 4. Securing dilithium for tomorrow. Real-world applications of post-quantum cryptography. Now, theory is awesome, but let's actually apply this to a concrete real-world scenario. The original lattice-based dilithium scheme is super widely respected because it only requires simple, uniform sampling over integers. It completely avoids those complex Gaussian distributions that are notoriously vulnerable to side-channel attacks. However, original dilithium doesn't naturally possess a lossy mode. So to make it definitively quantum-proof in the QROM, using our new framework, we actually have to modify its parameters. We have to increase the size of the modulus so that the underlying ring allows all small elements to be invertible, granting it that absolutely crucial lossy mode. But, security isn't free. Securing dilithium for the quantum world, creating what we call dilithium QROM, means the total size of the public key and the signature increases by a factor of a little over 3. Just look at the jump. The public key goes from a tiny 1.5 kilobytes up to 7.7, and the signature swells from 2.7 to 5.7. But honestly, that slight bump in data size is the exact cost of guaranteeing that your digital identity is safely, permanently rooted in the highly secure modular learning with errors, or module LWE problem. This tight reduction means that even against a full-blown quantum supercomputer, forging a dilithium chrome signature is literally as impossible as solving the module LWE problem itself. It's a completely necessary trade-off for true, provable long-term security. This paper is an absolute game changer. It brilliantly solves the Fiat Shamir vulnerability in the quantum era, giving us a tight, history-free proof framework and a highly concrete post-quantum scheme in dilithium chrome. But it leaves us with a massive, almost unsettling question to ponder. As quantum computers scale from just theory into our everyday reality, what other cryptographic foundations currently holding up our entire digital world are we going to need to rebuild from the ground up? Definitely something to think about the next time you see that little secure padlock icon in your browser. Thanks so much for watching this explainer, and keep learning.